Hey everyone. In this video we're going to take a look at a volumes of revolution question. So we're told consider the solid generated by revolving the region bounded by y equals ln of x, y equals 1, and x equals 1 about the line y equals 1. So the line y equals 1 is our axis of revolution. We're asked to write down two different expressions for the volume of this shape. So the first thing that you should always do, just sketch it out. So let's start by sketching the line y equals 1, or y equals 1 here. Let's go y equals 1 is about right here, and we'll do a line. Right, this is the line y equals 1, so this is where our axis of revolution. Okay, and then we've got the line x equals 1, so that'll be a vertical line. Okay, something like this. Great. X equals 1, and then we've got ln of x, and we know that ln of x has an x-intercept at x equals 1, so it intercepts the x-axis there, and then it's going to look something like this, right? And we can also label this point that it intersects as well, right? Because, well, when does ln of x, when is that going to be equal to 1? And we know that that's true when we have e, right? Ln of e, because it's a logarithm base e of e that will reduce to 1, right? Great. Okay, so what we are revolving is this red region, right? This is the solid that is generated by those curves, and the question says that we'd like to revolve it around y equals 1. So we will revolve it around this line, right? And that is going to create this interesting shape. You can see it's going to create some sort of like, almost like a little Hershey's Kiss like object, or like a little hat, like a little party hat. You can think of it in that way as well. But this is kind of the shape that we're going for. I'm not going to do a detailed drawing because I'm sure that there's some Khan Academy videos that can probably do a better job of visualizing this. But let's take a look. Like, in the first way that I want to consider this volume would be if we were to construct some vertical lines, or some vertical rectangles, I should say, like this, right? And this is like infinitely small, but I'm making it much larger for the purposes of this video, right? So this is going to have a thickness of dx. Dx is just a very, very, very small change in x, right? I think that it makes sense how we can see that that is that is the width of our rectangle there. Now, if we were to rotate this about this line, can you see how it's going to make just like a disc, right? It's going to make a disc that looks somewhat like this. Let me try to do a good job of drawing this. Something like this. Not the greatest drawing. I think I can improve this a little bit. Let me try that again. Make it a little larger, actually. Something like this. Yeah, here. This is a little bit better. Not an artist, but this here is our line that we're revolving around. Y is equal to 1. Okay, and we just said that this has a thickness of dx right? And our goal is we would like to find out what this volume is. This little red shape, this red disc that I've drawn. What is this volume? Okay. And, well, we have the thickness, so, I mean, we can just find the surface area of that, that circle, right? That top face. And we can multiply it by the thickness, and that will give us the volume of this red shape, right? So, well, we are going to need what is the radius of this thing. And we know that the radius, well, if you kind of look back at our drawing here, when I didn't realize I did not label y is equal to ln of x. Well, okay, when we are at x equals 1, we know that ln will be 0, right? So at that point, the radius will be 1, right? The distance from the x-axis to the line y equals 1. That distance will be 1. But as we get more and more closer to the tip of that shape, right? That's when x equals e. You can see that the radius of the disk that we are creating will get smaller and smaller. And in fact, well, we know that this height right here takes the form of ln of x, right? It's just the distance from x equals 0 to the function. So that means that the radius at any point between 1 and e would be 1 minus ln of x, right? So that represents the radius, okay? So this radius here, this is going to be 1 minus ln x, okay? Great. So what we can say is that this shape that we have, the shape that we've created, we call this dv, and this means differential volume. We call this a differential volume because, well, the dx, the thickness, is infinitely small. That is what that differential means, right? It's infinitely small. So this volume that we create is essentially an infinitely small volume that we create. And the goal is that we are gonna take these infinitely small volumes, and then we're going to take the addition of every single one of those from x equals 1 to x equals e. And then the sum of all of those will give us the volume of the entire thing. But the goal here, let's create an expression just for a singular differential volume. And like we just talked about, we said that the top face of that differential volume will just be pi r squared, which is pi times, and we just said that the radius at any point would be 1 minus ln of x. So pi radius squared times dx. Okay? So we have an expression for the differential volume. So that means that the integral, well, the volume of the entire object would be the integral of these differential volumes from x equals 1 to x equals e of pi r squared dx. So we've done one of the things that this question has asked us to do. It says write two different expressions for the volume, and we have just come up with one expression. So this, I believe they would call this like the disk method in like a calculus course. Honestly, I don't really like giving them names because it makes most sense to me to just create the differential volume using like understanding and then construct the integral however makes the most sense. Because you'll see there's a lot of different cases that you can run into. So let's do another case. So realize that when we constructed this expression, we did vertical bars with thickness dx. So let's see, maybe there's another way, and let's try doing it with horizontal bars. So let's try that. Let's scroll down. Okay. So the shape that we have here, same exact thing, right? Something like this, approximately. Not the greatest, but you get the idea. This time, let's consider doing some horizontal bars. Okay, and the horizontal bars, you can imagine that, remember, we're doing the sum of the infinitely small horizontal bars, which means that this height is going to be infinitely small. So just a tiny change in y. Okay, great. So what have we got here? Okay, so we're rotating this around y equals 1, right? So this is going to create this sort of shell, and I believe that they typically call this method like the cylindrical shell, because like it looks like we are going to create a bit of like a cylinder, right? So let me try to draw this. We've got something that looks sort of like this, right? Because we're just rotating that that tiny sliver of rectangle. Well, we're rotating this entire thing about an axis that is like quite far away from it, right? So it's going to create this kind of like outline of a cylinder, right? There we go. And then this is our axis of revolution. This is y is equal to 1. Okay. So what is this distance here? We are looking for this distance as well. Okay. Well, we know that this is, it goes up. It goes from x equals 1 to, well, this is y is equal to ln of x, right? So if we were to find the inverse of this, right, we could say that x is equal to e to the y, right? So this is just like the expression for x. For if we wanted to find out what the x value was at any y value of y equals ln x, then we would just need to do the inverse of that. So that's x equals e to the y. So it's a little bit different because remember that we are starting, let me scroll up. Remember, we are starting from the x coordinate, x equals 1. So if we just had e to the y, that wouldn't make much sense right away at our first coordinate, because we're going to start with a horizontal length of 0, right? So it would be like, I think it would be, e to the y minus 1. Yeah, that makes sense, right? So we've got e to the y minus 1, right? Because that makes sense, because at when we're at y equals 0, which is right here, that'll be e to the 0, which is 1. 1 minus 1 is 0. You can see we've got a horizontal like length of that rectangle here. That'll be 0 at that initial point. And then as we get to the closer and closer to the top, well, we know that that will approach e to the y, right? So as we approach 1, y equals 1, it will be it should have a length of e minus 1, right? And that it makes sense because we have e to the 1 minus 1, so e minus 1. So that makes sense for any value of y, right, in between 0 and 1, right? Let me make that clear, actually, that we are integrating now with respect to y. So this is from y equals 1, this is y equals 0. Great. Okay, sounds good. So how do we get the differential volume? This is what we're trying to figure out. Okay, so if we were to unravel this cylinder, you could see that we have got a shape that looks kind of like this. And let me actually draw this ever so slightly differently. it'll look something like this, right? And this was our original rectangle that we've constructed. So we know that it has a thickness of dy. It has a height of e to the y minus 1, depending on where we are from y equals 0 to y equals 1. The only thing we're missing now of this like rectangular prism that we've like unraveled, we just need to know what this long length is. And you can imagine them, well, this long length is going to be the circumference of the circle. Okay, so it's 2 pi times the radius, right? And what is this radius? Let's look up, right? Okay, well, the radius, we're looking for this green value, right? This is the radius. And the radius in this case will be, okay, well, it starts at y equals 1, right? So it should be 1 minus y, right? Whatever the y is, and in this case y is equal to, actually, yeah, it doesn't matter because we're with respect to y in this integral, right? So it is 1 minus y, right? So this is 2 pi times 1 minus y. Great. Okay. So we can finally conclude that we've got our differential volume. This is going to be equal to the volume of this prism that we have, which is 2 pi times 1 minus y times e to the y minus 1 times dy. Pretty ugly, but this is the differential volume. So if we wanted to know what the volume of the entire solid is, well, remember, we just need to take the sum of all of these, and we're taking the sum from y equals 0, right? This is where we start, and we end here, and this is at a value of y equals 1. So now we are going from 0 to 1 of 2 pi 1 minus y e to the y minus 1 dy. So we have successfully constructed 2 different ways that we can express the volume of this shape. This method here, which is often called the cylindrical shell, but honestly just go with your understanding. And then we also constructed this integral up here, and this integral was from this these little discs that we've created. Cool. So I hope this video was helpful, and yeah, good luck on all your final exams.